Okay, so we're going to start with introduction, and you heard a lot about acronyms: IWFM, IDC, C2VSIM, CalSIM. Maybe you know all of them. Maybe you're new to some of these acronyms. So I'll try to explain what they are in case you're new to all these models. Basically, IDC stands for IWFM Demand Calculator. It's a nested acronym. IWFM is a integrated hydrologic model, kind of similar to ModFlow, and stands for Integrated Water Flow Model. So IDC is IWFM Demand Calculator, and as the name implies, it's a demand calculator based on agricultural parameters as well as urban demand. And it basically routes on top of calculating the water demands, land use based water demands. It also routes the water through the land surface and the root zone of the hydrologic system, and we use physically based methods as much as possible. The methods we use are nothing new. We didn't develop these ourselves. These are basically methods that are taken from irrigation scheduling type models such as FAO 56. Maybe you're familiar with that, ET calculations and whatnot. We use the methods, most of the methods that are described there, but of course we twist some of them so that we can actually use IDC at much larger scales than FAO 56 methods were developed. And we are also interested in linking IDC to groundwater models such as IWFM so that we can actually calculate the recharge to the groundwater and the amount of diversions and pumping that is required to meet those demands. So to be able to do that, we do change some of the methods that are described in FAO 56. And essentially, it is the standalone root zone component of the integrated water flow model. And most people, like some people use IDC by itself. They're not interested in groundwater modeling at all. Like as I said, there are some companies who are using it to develop agricultural water plans, and they just use IDC by itself. Some people are interested in the full hydrologic cycle, especially lately because of Sigma. So they use IWFM, but the fact that IDC is kind of a Lego piece that is sitting in the IWFM, what they do is they first calibrate the IDC part of their large IWFM model, which runs much faster than a full integrated hydrologic model. And then once they're comfortable with the root zone part of it, with their demand numbers and whatnot, they just plug it into IWFM and they start calibrating the groundwater piece, the surface water and whatnot, trying to get the diversions and pumping to meet those demands. So that's how people are using it. Okay, so again, IDC actually kind of spun off from IWFM. One second, let me. Okay, perfect for sleeping, right? Okay. So, if you ever looked at our documentation, IWFM documentation, you'll see this picture. We try to kind of represent the components of hydrologic cycle that we simulate in IWFM. And IDC is really the part that basically simulates this yellow area, the land surface flow processes, as well as the root zone, which is this dark, part of this, picture. In a much simple way. So if you kind of take each of the hydrologic components that we simulate IWFM and turn them into some kind of Lego pieces, that's how it looks like. Our conceptualization of hydrologic system in IWFM. We have streams, lakes, the groundwater component. There can be a vadose zone, unsaturated zone, and then the land surface and the root zone part of it is called IDC, again, IWFM demand calculator. So basically, when IDC is used within IWFM, once IDC calculates the demand, since it has connections to the streams and the groundwater, it also gets information from the stream component in terms of how much diversions that are happening. and also from groundwater in terms of pumping, how much pumping is happening to meet those demands. So in a modeling exercise, it's possible that you have the demand that is calculated by IDC, but maybe you don't have the water in the system. Maybe you don't have the stream flow to meet that diversion, or you don't have the groundwater storage to meet the pumping. So IDC has that information, and when you again use IDC as part of IWFM, sometimes your supply doesn't match your demand. And if you're taking the IWFM workshop next month, we'll talk about how IWFM gives you some options to match the supply and demand. But by itself, IDC, since it doesn't have any information about stream flows and it doesn't have any information about the groundwater storage, it basically assumes that the demand that it calculates is met at all times. So essentially, when we're talking about IDC, water demand and supply are kind of same, synonym to each other. Except there's one option in IDC where you can basically tell IDC, well, don't calculate the demand. I'm just going to enter the demand. Basically, let's say these are contractual demands, right? Let's say you're assuming that the farmer is actually taking their water from the stream because they're entitled to, and that actually happens in real life. They don't want to basically let go of that water right. So then, your demand and supply will not be equal, but IDC allows that too. But that's, again, in the realm of IDC, it's kind of a, kind of an obscure feature. So the historical background for IDC, Bureau folks are talking about calcium. Basically, in DWR, we have this model called calcium. It's also, Bureau is, DWR is maintaining the Sacramento Valley portion, and the Bureau is maintaining the San Joaquin portion of it. It's essentially a reservoir optimization or reservoir operations model, calcium. So what calcium needs is the downstream demands, among other things, regulatory environment and environmental constraints and all that, environmental flows. But essentially, given those downstream demands, what calcium tries to do is it tries to figure out, how to operate these upstream demands. How much water to release from the reservoirs. And I hope I'm not putting my foot in my mouth. That's my understanding what calcium does. I don't do calcium, but generally, I think that's what it does. And essentially, it tries to figure out, the whole idea is, okay, meet the demand in the valley at the same time, manage the salt in the delta so that water, there's some regulations how much, the water quality, and then, that gets pumped into to the south. So we have like several tools. Calcium is one, and we have another tool called C2VSIM. This is the application of IWFM to the Central Valley. It's a fully integrated hydrologic model, again, of the valley. And there's some data communication between C2VSIM and calcium. C2VSIM basically produces stream aquifer interactions, historical stream aquifer interactions, which is an input to calcium. Also, C2VSIM has the demand calculation inside, and calcium requires that demand. So basically, about 10 years ago, 12 years ago, we said, well, let's try to streamline these tools, because there's a lot of data translation used to happen from C2VSIM to calcium. We wanted to actually make that data flow as easy as possible. So that's what IDC, that's how IDC started. We basically said, well, let's take out the root zone component of IWFM and then use it as by itself to basically calculate the demands for calcium. So that happened in, I think, 2005, 2006, almost 12 years ago. And then the first version of IDC, very quickly we realized that it didn't have everything we wanted to have. Like, for instance, it didn't explicitly simulate rice and refuge operations. As you know, they pond the fields for rice. We didn't have that in the original IDC. And the methods that were used in IDC to calculate the demand were not really compatible with daily calculations. You know, like our cultural practices are basically, you know, daily, right? I mean, not necessarily monthly. So we wanted to be able to capture those practices at the characteristic time that they're being applied. So the methods that were originally in IDC were good for monthly runs, but not good for daily runs. So, and also some of the data that IDC needed didn't really correlate with the real world, you know, that they were kind of like calibration knobs. It wasn't easy to take it and apply it to somewhere else. So basically, after seeing those shortcomings, we basically ended up developing what we at the time called IDC version 4.0. Now, for those of you who are familiar with ModFlow, you know how ModFlow has all these packages and they have like 3-letter names, you know, SFR and RIV and stuff like that. So we don't use the letters, we just use versions. You know, you'll see that, you know, it's all about version numbers in IDC and IWFM. So basically, we ended up coming with IDC version 4.0, which addressed the RICE simulations, refuge simulations, and also, you know, were capable of doing daily runs with the available data. Over the years, IDC became a container. Now we have several different ways of simulating the root zone. You know, over the years, people ask for, well, you know, I have this kind of application, can you do that? You know, so we said, well, okay, let's put that into IDC. So we ended up, again, just like, you know, how ModFlow works, we ended up with a bunch of different IDC versions. But now IDC, when you download IDC, it's just a container which has all these different components in there, and you choose which one you want to use depending on what you want to do. And you don't have to memorize all those version numbers. You know, at the beginning of the documentation, which can be downloaded from our website, you know, there's a table that kind of summarizes each of the versions and which one does what, and you just choose, you know, one or the other. And they're basically not too different. You know, there's just like 1 or 2 small changes from one to the other, Okay, some of the projects using IDC, again, you know, and the earlier version of IDC was using Calcium 3 project, and, you know, again, listening to the Bureau folks, you know, you're here to learn what calcium hydro is doing. You know, like the reason why it's calcium hydro is calcium hydro, not IDC, is because of the limitations that I talked about. So now we have IDC, the original version of IDC, but now there's a RICE component, right? Since we're not doing it in IDC, in the original IDC, and there's several other things. So that whole thing is called calcium hydro. And generally speaking, the methods that we're going to talk about today applies, you know, to a certain level to the version of IDC that's in calcium hydro. But the one that we're going to talk about today and tomorrow is a little bit more advanced than what is in calcium hydro. And I've been telling the calcium folks, you know, are you interested in, you know, switching to the latest version of IDC? But they've been working on it for 12 years. They don't want to like just abandon it and then, you know, start another 12-year project. So I think it's going to stay there for a while. But again, so, okay, IDC, earlier version of IDC is in calcium 3. RMC, which was much easier to pronounce than Woodard and whatever, I can never remember. They basically, for one project, you know, they basically took IDC and ran it by itself and generated input data to a ModFlow model, you know, the recharge and pumping. You know, it was used in Idaho for the Idaho Department of Water Resources, again, to calculate, you know, future water demands. Glen-Colusa Irrigation District used it. There's a model out there called SACFEM, Sacramento Valley Finite Element Model, which is a micro-FEM model originally. It's developed by Bureau of Reclamation, I believe, for water transfer projects. And micro-FEM itself is a groundwater-only model, so they're using IDC to calculate the pumping and recharge again to microfam. There was a UCD master's student, he used IDC to calculate the Delta Island consumptive use values for Fabian Tract and Staten Island. For those of you who are familiar with the consumptive use model, they were saying that, like IDC can, replace the CU model to basically, look at the situation a little bit more in detail, but that didn't come to fruition. And there are several agricultural water plan, management plan programs that are developed by IDC, and there are several IWFM models out there, and more are being developed right now that use IDC. The reason why I'm listing all these is because just to assure you that IDC is not an obscure model that DWR developed it and only DWR uses it. It's starting to be really basically gaining traction, partly because of Sigma. But even before the word of Sigma was out there, people were starting to use it. So if you, again, most of you guys are here, I think, just to learn and maybe decide if you want to use it or not for your projects. You're not going to be the only person using it. So I know at the beginning people were really scared. They just didn't want to be the first people using that. But it's not the case anymore. And the good thing is, a lot of these projects, I just did a search on the internet, and they just came up. So people are able to pick up the resources that we provide them on the internet, like our documentation, the sample model, and without even having to come to us and asking for your technical assistance, they're able to develop the tool. So apparently whatever we are doing is working to help people out. But we are here to answer any questions, of course, in terms of technical assistance. Okay, some of the features of IDC. This is kind of the summary of what we're going to go through for the next 2 days. It uses a computational grid, right? It can be a finite element or finite difference grid. But if you want to use a finite difference grid, you still have to represent it as if it's a finite element grid. You can do that. But we don't use the methods, finite element method or finite difference method to solve the equations. We just use that grid to represent the spatial distribution in the input data. This can be your land use, this can be your precipitation climate data, soil properties, irrigation management. We basically use that grid just to represent the spatial distribution of the input parameters. Again, we simulate land surface and root zone flow processes as well as the water demands, and we do that at each grid cell, but also each grid cell can have multiple land uses. So our computational unit is actually sub-grid cell, and we'll talk about that. We are using irrigation scheduling type approach. We have direct representation of rice fields. You have the option of basically simulating 3 different types of rice. I mean, the rice is the same, but in terms of how they're managed, their decomposition, there's some differences. We can simulate, rice with flooded decomposition, non-flooded decomposition, and no decomposition. So for instance, flooded decomposition is, again, I'm not a farmer myself, but talking to people, after they harvest the rice, sometime in September, they basically, flood the fields, up to 6 inches or something like that, so that they can basically decompose whatever is left over from rice. Non-flooded decomposition is they don't flood. I think they just, like irrigate like 2 inches or something like that, that just, like moist the soil and then again, like let the rice decompose. And no decomposition is basically there's no water involved, which is, I think, pretty rare right now. Apparently up until mid-90s, they used to burn rice in California. I wasn't in America then. But if you have a historical IDC run, you have the option. And you can actually, throughout your simulation period, you can switch from one land use to the next. It allows you to change your land use types over the simulation period. We have the ability to simulate regulated deficit irrigation. We have one example. One of our sessions is dedicated to that. Some other kind of, additional features. Riparian vegetation access to stream flows. This is when you're using IDC linked to IWFM. So if, for instance, you don't have enough water in the system, you can basically assign riparian vegetation to stream nodes to, take water from the stream to meet their ET demand. And we have the simulation of evapotranspiration from groundwater. Okay, we do urban water demand as a function of population and per capita water use. If you are using IDC as part of IWFM, you have the option to deliver water. So, you basically calculate demand at each cell, but then, again, as part of an integrated hydrologic model, now you need to meet that demand. And depending on the information you have, you can say, well, I have this diversion, and that diversion meets the demand at this collection of cells or this individual cell. So depending on your understanding of the system, you have different ways of distributing the supply of water within the model area. We simulate ET of applied water as well as the effective precipitation, or ET of precipitation. We do reuse, like sometimes there's the, agricultural tile drain, or, agricultural tail water return flow, or the runoff from the urban area. Sometimes these water are captured and reused, depending on the system, so we can simulate those. The default is that IDC calculates the water demands dynamically, based on your soil properties, your climate data, your land use, your irrigation. But you can also tell IDC, well, forget about that physical demand. I have this contractual demand, and I want to see when I apply that much water, what happens, right? Like, do you increase your recharge, for instance? And generally, that's the case. That why people apply more than what they actually need, what their plants need. So you can do both of those. And again, during a simulation period, you can switch between the two. So it allows you. So there are all these options, but having these options also make the input data files a little bit complicated. The more features you put in, the more difficult it is to understand what you did, a year ago. So we have, extensive water budget outputs for soil moisture and, for land and water budget, which is essentially the equivalency between the demand and supply. Like, are you meeting your demand with your supply? And we also have the root zone budget, which is really the mass balance budget for the root zone. Recently, we also came up with a new type of budget. Again, for those of you who are familiar with the ModFlow, ModFlow has this zone budget. So we now have that option. We used to have it only for groundwater, just like ModFlow, but because of Sigma, people are so interested now to zoom into, like whatever area they want to do, they want to look at. So zone budget allows you to do that, not just for groundwater now, but also for land surface, for the land and water use, as well as the root zone budget. Okay, so when I first developed this, again, the idea was to somehow use it in calcium. So at the time, I developed it as a tool that you can actually, run it by itself. You just say idc.exe, and then it runs, or you can link it to as a dynamic linked library for those of you who are into, computer programming and stuff. So you can also link it to your model, whatever it is, and kind of invoke the functions of IDC from your model. So possibly we can do that from calcium or from any model. So essentially, if you do that, IDC basically calculates the ag and urban water demands and passes that to your whatever model that is. And if your model has a stream module and a groundwater module, it basically communicates with those modules. So that's how it is envisioned. Of course, this part would be up to you guys if you're interested in doing something like that. Okay, so that's basically it. Do you have any questions so far? No? Okay. Yes, John.
When you mentioned the delivery of water to a subregion or to individual cells, subregions being fairly large in concept, can you elaborate on doing it for an area rather than...
So in IDC and IWFM jargon, subregion is any collection of cells within your model area. And how you organize those cells and group them is completely up to you and whatever they might mean. So for instance, let's talk about the GSA that has multiple entities, right? This is a multiple group. Or it could be like different sources of water. That's what we have, for instance, in calcium. Like some areas are only served by surface water, some areas only served by groundwater, or some areas by both. So it kind of depends on your needs of your model, and you define, you list your elements, and each element is assigned to a subregion. So how you define those subregions is up to you. But again, generally subregions represent some kind of a operational boundary, water supply boundary. Anything else? I mean, you guys use IDCs.
On the lines of, say, it's a irrigation district, and they're running water through a delivery canal. So one easy concept is to create the irrigation district as a subregion. But you've got individual turnouts, and so say I've got grower A, and he's got 160 acres. I'm just sort of getting at, do I need to define that 160 acres as a subregion as compared to, say, then, or instead telling it, I'm going to deliver water off that diversion point off to this, and this element?
Yeah, I mean, in that case, I would not go for that detail. Like 160 acres, I know that there's a single diversion that goes to that. I mean, you can do that. I mean, if you have that much data, you can do that. But generally, at the scales that we're talking about, people don't have that much data, right? So they know where the diversion is taken, right? And they know that it is kind of, distributed through canals and stuff like that. But sometimes they do, sometimes they don't have how those canals are distributed in the area, or even if they do, maybe it's just too much information to include in the model. So generally what they do is, okay, I know that there's this diversion at this location, and here's this area that diversion eventually serves, right? And then they say, okay, that diversion goes to this group of elements. And if those group of elements, whatever that boundary is, if it stays the same over your simulation period, then that's a candidate for defining it as a subregion. Then you can say, my diversion 10 goes to subregion 5, right? And then IDC or IWFM, in that case, will do the internal distribution of that diversion based on the demand. But if you have the information, well, I know every single field, I know every single farmer's demand historically, the district gave it to me, but my understanding is even the districts don't really have that kind of data, most of them at least, then you don't go to that detail, because eventually that becomes a nightmare. As I said, you have the option, but people don't go to that detail. Does that answer your question? Yeah.
Yeah, what's the scale of use for this type of model?
So generally it is water district or county, right? Generally multiple water districts. We have done one project with UC Davis at a field scale, but generally that's not common. It's not a field scale model. It's basically, water district and up.
And what limits the scale in this approach?
It's really the detail. At the farm scale, I mean, you're talking about, let's say, farrow irrigation. Like how much time does it take when you put the water at the beginning of the farrow and goes to the end. We don't have that kind of detail simulated in this. You might be interested in like two-dimensional distribution of soil moisture. You know, we don't have that kind of detail. Or like, you know, like how the irrigation non-uniformity over a single farm. We don't have that kind of detail. So, so you can use it, but then you basically applying the simplification assumptions that we are using at the farm level. If that's what you want to do, that's fine, you know, but, you know, generally that's not what people use it for.
Could you briefly touch on the time step?
Yeah, so theoretically speaking, you can go down to a minute time step, but because of the available data, most people use it on a daily time step. I mean, like precipitation, you have it hourly, maybe even less, you know, less than hourly, but then a lot of the other information that you need to run IDC is not at an hourly time step. So, you know, even some of the data daily is becomes an issue. Like ET, for instance, you know, it's not easy to get the ET data at the scales that we're talking about unless, you know. So generally daily and up. I know, can I call you guys RMC? It's so much easier. RMC, you know, uses it at a monthly time scale. So generally daily and monthly, they are the two common time steps. There was a question? Yeah.
Yeah. Has it already been compared with other benchmark models to validate its capabilities?
So that turns out to be very difficult. I mean, we have done some work with the USGS folks, you know, like they have their farm process. But the thing is, the equations that we solve here and the assumptions are so different, you know, between farm process and ours, that it proved to be really difficult. You know, like it's really hard to start, okay, we know that there are differences, but where is it coming from? So what we are doing right now, and with UC Davis, is they have measurements at Scott Valley up north, field level, right? So we are basically working with them and running IDC at 8 sites, alfalfa fields, to see if we can get the water demands and right, you know, and also, I mean, they don't have the recharge, of course, but they have measurements, soil moisture measurements at every feet, I guess, up to 8 feet. The initial results are good, you know. So comparing it to other models didn't work out, which is, you know, interesting. It just, again, because of the equations that are being sold and all the assumptions that different models make and how they don't match to each other. But I'm hoping that comparing it to field measurements is the ultimate verification.
Or maybe versus a lysimeter where the recharge is already known, so I'd like to see how IDC can estimate the recharge coming down on the lysimeter.
Yeah.
Has it been done
Mm-mm.
in comparison?
Yeah. Yeah. I mean, yeah.
What is the time stepping up there in the sky?
Daily. Yeah.
I'm reminded of a project, interestingly, I did in Mojave some years ago where we were doing hourly because we had all things were wet, pinned against the fall. And the pumping hourly was phenomenal at the midday heat. Not sure why I want to know hourly, but it strikes me that when you're looking at riparian vegetation like that and the stream bank kind of buildup would be very relevant to the sky.
Yeah.
It's an interesting question. What's the time step?
Yeah, I mean, when you're talking about, you know, stream bank going, you know, like expanding and shrinking, I mean, we don't, I mean, in IWFM, even in IWFM, we don't have the type of detail that you're talking about. I mean, you know, we are not looking at like streams kind of, you know, widening, and if that's what you're talking about, you know, yeah, we don't have that kind of detail. So again, you know, you can, theoretically speaking, you can run IDC down to a minute time step, but again, I don't know. Nobody has done it. Maybe, you know, there's going to be an opportunity and we'll hear about it.